this is a formula that calculates the balance of some amount you might invest in either a bank account or some type of investment. And this is where you have what we call monthly compounding, meaning your interest rate, in this case 2%, they take 1/12th of it, and each month you're compounded 1/12. So in other words, when we were looking at this the other day, we would say, okay, you got a 3% raise a year, so you would calculate 3% of the old salary to get the new. So here they take 0.02 divided by 12, and each month that's what they multiply the investment by. Okay, so each month it's growing by a little teeny bit. So N here is 12. That's what compounded monthly means. So when you're filling this out, these two words right here correspond to N equals 12. P stands for the original amount you invest, which is called your principal. Many of you are in our BAT program, so you know that. And in this case, what's P equal to? 5,000. And you want to see how long it's going to take. So how long is really the question of the next 2 days. How do we figure out how long? We're trying to figure out how to solve for T. That's what we're trying to figure out, how to solve for T. And we want to know how long it's going to take for this amount of money to grow to 7,000. So A is going to be 7,000. When our interest rate is 2%, so R equals 0.02. So if we put all that together, we get 7,000 on one side equals 5,000 times 1 plus 0.02 divided by 12 raised to the NT. N again is 12 compounding periods per year times the number of years T. So this exponent up here is the time. So I asked you to solve this problem. What were you able to do it? Yeah? How did you do it? Okay, you simplified what was inside the parentheses, and what did you get for that, Claudia? 1 point. And in this case, I would really strongly urge you, when you're dealing with really large sums of money, to be more precise. 0.002, it was really 0.0016666 repeated, right? So I'd carry it out a few places just for precision and accuracy. Okay, then what you do, Claudia? What did you raise to the 12th? Yeah. All right, so you basically used your exponent properties here and raised this to the 12th, and then that would be raised to the T power, since when we have a power to a power, we multiply. Okay, so that's interesting. Okay, let's see. And then what did you mess up with?
I didn't raise it.
Oh, you forgot the T? Okay. So let's suppose we did that. Let's take that number and raise it to the 12th power. I mean, let's see what we get. I'm going to open my calculator here. It's probably hiding behind here. Where is it? I'm going to have to close it and then open it. So let's see what we get when we raise that. I'm going to put the whole thing in 1 plus, so I can be as precise as possible since my calculator is doing all the work. Raised to the 12th power. Let's see what that is. 1.020184, blah, 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 blah. Anybody remember that? Let's see. I don't have my little, I can get my camera out, but let's see. I'll take a picture. All right, so now we get that amount. And let's cut and put that in our little problem. Cut it, and we'll paste it right back here. So now we have 7,000 equals 5,000 times, let's plunk that in, let's paste it. That amount, make it a little smaller, raised to the t. Now what? We're trying to solve for t. Now what do we do? Divide both sides by 5,000. That sounds like a good idea. 1,000 is a common factor to top and bottom. 7/5 is 1 2/5, so that's 1.4 equals, let's copy that again, paste it. And so now we have 1.4 equals that number raised to the t. How are we going to solve for t? You're allowed to square root t on both sides. There'd be nothing wrong with doing that as long as you do it to both sides. But that would just, square root means to the 1/2 power. So that would give us t divided by 2. So it's perfectly legitimate to do that. It's not going to help us solve for t. Oh, it's sort of like doing division when you have multiplication. What the heck's Victor talking about? See, I paid him to say that. No, not really. So Victor says it's kind of like doing division when you have multiplication. So what he's thinking about, I think, is if you had a simple equation like this, to solve that equation for x, you undo, right? You undo what's happened to x, which is x has been multiplied by 3 by dividing both sides by 3. So that's called what are those operations called? Multiplying by 3 and dividing by 3. Inverse operations, right, Ian? So it's like that exactly. We want to undo multiplying by 3, so we divide both sides by 3. So what do we have to undo here? We have to undo raising 1.020184356 to the t power. I have to undo that. I have to get t out of the power, right, as an exponent. I got to get it down so I can solve it like an equation. I have to know the inverse of exponentiation, because that's what we're doing. This is called exponentiation when you raise something to a power. I need to know the inverse of exponentiation. Guess what? I don't know that yet. The only thing you could do right now is put 1.4 into GeoGebra and get a horizontal line, put that function in and see where they intersect, or put it in your graphing calculator to find the value of t. Or you could do a guess and check and just try to get as close as possible. But algebraically, we don't know how to undo exponentiation. We don't know how to solve for t. So that's why today we are going to do liftoff. Okay, liftoff, Houston. So let's consider one of our basic parent functions that's exponential 2 to the x. I think we know a lot about 2 to the x. Here's a picture of it. So let's take a little quick review since we were on Thanksgiving break. What do we know? How do we know that 2 to the x, the function f, has an inverse? What is it that tells us this has an inverse when we look at its graph? That's right, Nick. It passes the horizontal line test. So yes, it has an inverse because it passes the horizontal line test. Perfect. And when it passes the horizontal line test, it means that the function is 1 to 1. And what that means is if you have different inputs, always have different outputs. Unlike our parabola, different inputs have some similar outputs. So it's 1 to 1. It passes the horizontal line test. Let's review what the domain of f is and what the range of f is. Okay, so what's the domain of this function? Right, all real numbers, negative infinity to infinity. Any number along that x-axis is allowed to be the input for x. When it's a negative number, our output is really, really small. In fact, as x gets really big, we can see as x goes towards negative infinity, this line is getting really close to 0. That's our horizontal asymptote. What about the range? Someone other than Victor want to tell? And Ian, Eric?
Parenthesis 0, positive.
Right. What do we call those kind of number? Parentheses 0, infinity. All positive numbers, right. For once we get to say all positive numbers, because all semester We've had to train ourselves to say non-negative because we've been including 0 a lot, right? But now 0 is not a possibility for the output. So our output is all positive numbers. So if you want to think a little bit into the future, meaning half an hour from now, you may want to think about what the inverse of this would look like. What would be the domain and range of the inverse? Just review a little bit in your mind as far back as you can remember about inverses. And if you forgot, then you can always take a peek at the first number 1 in the demo. Yeah, the range and the domain reverse each other, right? So, but we don't need to go there right now. It's, oh, hey, what happened to, that's weird. Wasn't I just writing all that? Oh, I guess I have 2 of these on here. Okay. All right, so we don't know yet how to undo exponentiation. So let's just call the inverse function of 2 to the x, we're going to call it g instead of f inverse. You know how that can get confusing with all those negative scripts and stuff. So we're going to say use the letter g to denote the inverse of this function. Again, we don't know what it's called, we don't know what it is, but at least we can play around with it. And we know since f of 3, if I put a 3 in here to the function f, so if I make myself a little table, here's x and here's f of x. If I put a 3 in for x, then my output is 2 to the 3rd. So what do I know about the inverse? Well, here's my inverse over here. So my inverse says you take the output from your first function, you put it into your inverse function, and what comes back? What do I arrive at? 3 goes into f of x, I get 2 cubed. Now 2 cubed goes into my inverse function. What's my output? 3. Right, you're right back to where you started. That's what inverses do. They undo each other. So you get right back to the original input was 3. The output of your inverse function is the same. This was that round trip idea, right? The round trip idea. You're right back to where you started, like Groundhog Day, right? So I take my output from my first function, which we could call 8. I'm just going to call it 2 to the 3rd, because I think you'll see a little pattern going on here. And the inverse function of 2 to the 3rd is just 3. Okay. Now, if f is 5, let's put a 5 into my exponential function 2 to the x. I get 2 to the 5th. So now I put 2 to the 5th into my inverse function. And what do I come back to? What's my output going to be? 5. Right back to where I started. Just like, it's exactly how input functions work. Okay, since f of negative 4 equals 2 to the negative 4, 2 to the negative 4, when I put 2 to the negative 4 into my inverse function, what is my output? Negative 4. Okay, so this is how this inverse function is going to act. And what's going to be really cool is when I figure out whatever the inverse function is, I'm going to be able to put this number raised to the t power into my inverse function, and I'll get my t out. Okay, I'll be able to solve for t once I know what the inverse is. I still don't know what the inverse is. So let's see here. So we're going to call this function g the liftoff function. That's what we're going to call it from now on, the liftoff function, because all it does is literally lifts off the function of that base. It just lifts it right off. It brings me back to my original input. Remember, what was the original input? The original input was the exponent. So all of the answers to this inverse function is just an exponent, your original exponent. That's all it is. No matter how crazy it looks or what kind of fancy names we get, the end result is just an exponent. That's all it is. So let's use this liftoff idea on these 3 problems. So let's lift off, that's what g means. Let's lift off the exponent of 5 to the 4th. What's my answer here? 4. I'm just lifting off my exponent. The next one, someone want to help me with that? Angela, can you help me with the next one? 2 divided by 7. It just says lift off the exponent. That's how I'm going to start interpreting G, lift off the exponent. And the next one, Eric, lift off the exponent. -2. And any volunteers for the last one? Lift off the exponent? -1. All right. Okay, so far so good, right? Not too bad, right? No need to panic. All right. All right. So that's Victor's idea. So I'm going to skip that and go to this part. Wait a minute. Where am I? I'm supposed to be on my addendum. Is this the next part of my addendum? No, I need number 6. Something happened here with when I put this in. Oh, there it is. Okay. So what if the input for the liftoff function isn't already in nice exponential form? So we can't just look at it and lift off the exponent. What's a student to do? This says lift off the exponent. So what would you put inside these parentheses? Not for the answer, but what would you put in for the exponential form right here? The input, remember, this is the input into your G function. What would you put in there? 1? Just number 1 like that? Oh, 9 to the 1. Oh, okay. Now I got you. All right, so I'm going to put in 9 to the first power. So G says lift off the exponent. So my answer is 1. Okay. Anybody got a different idea? Huh? To the x power. What to the x power? Never mind? Okay. All right. All right. Well, Claudia's shouting out, couldn't I have rewritten it like this? 3 to the second power? Could I write it that way? And then what exponent am I lifting off? 2. Let's review a little bit of other basic algebra here. See if you can figure out what this one would be. Could I have written it as 81 to a power? Which one? 1/2, right? That means a square root. So look, here I've got this input. Here's my x value, 9. I can go to 1, I can go to 2, I can go to 1/2. Houston, we have a problem for liftoff, right? Why is this a problem? There's multiple outputs, so what's the problem? This isn't what? It doesn't pass a vertical line test, right? So what's the problem? Not a function. Right now, it's not a function because I can take 9 and define it, in this case, 3 different ways and have 3 different outputs. So my input's 9, and I don't know what my identity is for my output. Oh, no. Big problem. Same's true with this one. So let's examine this one a little further. The last example should convince us that we have a problem. The power that we're going to lift off, whatever power we lifted off here, depended on what its base was, right? In this first one, when the base was 9, we lifted off 1. When the base was 3, we lifted off 2. When the base was 81, we lifted off 1/2. So we definitely have a problem. So to make this problem go away, we're now going to tell our liftoff function what the base is by using a little subscript that sits just like a little bit below G to the right. This is going to tell us what the base is for this input. So my input into this first function, into my liftoff function, is 16. I want to take 16 and write it as 2 to some power so I can lift off the power. So 2 to what power is 16? 4th power. So 2 to the 4th. So G says lift off the exponent when the base is 2. So here's my base of 2. Here's my exponent. I'm going to lift it off. 4. Perfect. So this has one identity because I know what the base is. And how about this one? Lift off the exponent when 16 is written as 4 to some power, when my base is 4. So that means 4 raised to the 2nd power. So I lift off the exponent when my base is 4, and the answer is 2. No quandaries at all. You know exactly what your answer is because you know what your base is. All right, the next one takes a little bit of thought, and I'm going to let you play around with that for just a few minutes at your seats with your, either on your own or with your group to see what you come up with for the next one. So the base is 1/2, so that's what appears here, and the exponent is -4. So when I lift off the exponent, my answer is -4. Okay, so let's review how you would do that algebraically for those of you who were a little confused. So I think what happened was with the 256 idea is that some of you were thinking the base was 256 and the exponent was 1/2. So the square root of 1/2 is 16. I think that's what you might have been thinking, but is that true for those? Yeah, okay. So, but look here, the base of this liftoff function is 1/2. It's 1/2. So you're trying to figure out 1/2 to some power, let's call it x, you could call it question mark if you wanted. 1/2 to some power has got to give you a 16. So that's your job. What power do I raise 1/2 to get 16? Well, you can do this a couple of different ways. You could take 1/2 and write that in exponent form. It's 2 to the -1, because that 2 to the -1 just says, hey, I'm the reciprocal of 2, which is 1/2. So you can rewrite that as 2 to the -1 raised to the x power. Okay, so far with me? Then your exponent rules say when you have a power raised to a power, you multiply those exponents. So this now becomes 2 to the -1x equals 16. So now your job is, if possible, to rewrite 16 so it has the same base as the expression on your left side. So 16 is 2 to the what? 2 to the 4th with a yawn in between, okay? 2 to the -1x equals 2 to the 4th. So now you have an equation. And since your bases are equal, since both sides have the same base as 2, to solve this equation, you just set your two exponents equal. So you're trying to determine when does -1 times x equal 4. So you divide both sides by -1, and x is -4. Okay. So when you get to the problems, the liftoff problems, where you can't just look at it and determine it, you just go through this algebraic process. You take the base, you raise it to the question mark, x question mark, you set it equal to whatever your input is, then you rewrite both sides of the equation so you have the same base, and then you solve for the exponent. Since remember, all our answers here are exponents to the liftoff function, that's all they are. All right, so here's a little tougher one. Okay, let's take a look at this together. We're going to go through this same process. All right, so we have g, the liftoff function with a base of 8, and the input is 16. So we're trying to figure out 8 raised to what power is going to give me 8 raised to what power is going to give me 16? That's what we're trying to figure out. I just did one of those run-on sentences here, which I can't do. So that's what we're trying to figure out. What is the question mark? So to solve that, we say 8 raised to what power gives me 16? 8 raised to what power gives me 16? So automatically, how do you think about this? Instead of panicking, you can at least get a sense. You say to yourself, well, if I raise 8 to the first power, I would get 8. And this is bigger than 8. If I raise 8 to the second power, I'd get 64. And this is a lot smaller than 64. So I know my exponent has to be a fraction between 1 and 2. So at least you start to hone in a little bit on what your exponent is that you're going to lift off. So let's go through the same process that we did here with this problem. So we're going to say 8 raised to some power gives me 16. So the question is, can I find a base that I can rewrite 8 using and rewrite 16 using? Can they both be rewritten with a common base? And if so, what is that base? 4? Well, I first heard 4, so let me go with that. 4 to what power gives me 8? Square root of 4 is 2. You could, but it's going to be another fraction. All right, so I could write 8 as 2 cubed. Is that a good base to choose? Can I write 16 as 2 to some power? Yeah, to the 4th, right? So let's rewrite both bases right now as 2 to some power. So 8 I'm going to write as 2 to the 3rd, and I'm going to call my question mark x. And I'm going to write 16 as 2 to the 4th. Oh, that's looking a lot better right now than it did a few minutes ago, because now I use my exponent rule that says when I have a power to a power, I multiply my power. So I get 2 to the 3x is got to equal 2 to the 4th. And since my bases are exactly the same, I've rewritten them so the base is exactly the same, 2. Then all I have to do to solve this for x, I just set my 2 exponents equal. 3x equals 4. To solve that, I get x equals 4/3. So let's review our rational exponents for a second. This says 8 to the 4/3 equals 16. Let's see how that works. Let's jog our memories a little bit from the first class when we were working with rational exponents. Remember, it's winter. We've harvested all our root vegetables. They go in the cellar or some cold, dark place. In the cellar, the denominator is the root. So this says the cubed root of 8, which is 2, and then 2 raised to the 4th power, which is your numerator, is 16. So this is the same thing as the cubed root of 8 raised to the 4th power, which is 16. So now I say lift off the exponent for 16 when the base is 8. That's what all this yucky length, all this notation means. Lift off the exponent of 16 when the base is 8. So you rewrite the base is 8 to the 4/3. So your answer here is 4/3. What would I put as a decimal? The 4/3? You just have to write it as 1.3 with a little bar above it. Okay. If you write it as a, yeah, 4/3, because I'd like to see what the root is. As a fraction, when your exponent is a fraction, then you can see it as, you can see what the root you're taking, and you can see the exponent you're raising it to. When you write 1.3 with the bar, you're going to have to convert 1.3 over to a fraction anyway. So, but if you wrote here 1.3 with the bar like that, then they're equivalent. So I know that it's the same answer. But the preference would be, if you could, to use the fraction. Does that make sense? Okay. All right. So in the last line of the chart, I didn't put the chart in. As you can see, I've made an addendum to this class notes. I didn't do the class notes as they were written. This is how I used to teach liftoff function idea. And we would have a chart where you'd go in now and fill it in. But we've just filled in a bunch. So what did we just see? We saw that when we have the liftoff function, when we're lifting off the exponent from x, whatever x is written as b to some power. And so when we lift off the exponent, we write that as our answer. So what does that mean? It says the same thing as we take this base, b, we write it to this power, because this is the power, and we get our input into our inverse function. So this is the general definition of a lift-off function. Lift off, L-O-G, lift off, is a log. So all a log function is lifting off the exponent. When you write your input, call it x if you want, call it y, call it whatever you want. When you write your input as b to some power, you're lifting off the power. So if we go back to our properties, again, the x and y can switch here, it doesn't matter. The log base b of x, if it equals y, so it's a if this is true, then your base of your log raised to the exponent you just found brings you right back to where you started at x. You could also write it this way. B to the x, if you prefer this, b to the x equals y means log base b of y equals x. So a lot of people like thinking of the exponent as your original function, where that was your input, x. So you got some point here, xy. Then remember, with your inverse function, you reverse your inputs and your outputs. So log base b of your output brings you right back to your exponent. Okay? So the liftoff is simply getting back to your original input. So if I were doing this problem that we just did a minute ago, if I have it here, do I have it somewhere? Oh, I got so many pages. Was it one point? I'm trying to find. Oh, here it is right here. So if I'm trying to solve this, what's my base? Put this into log form now. What's my base? My base is this long, big green number here, right? I taken from my calculator, so let's copy it. So to solve this, I need a log. So let's solve it. Log, right, with this base, I mean, it's kind of nasty, but so what? We can at least log of that base. What's our answer? 1.4. And that's going to give us t. I'm trying to solve for this thing. So I take the log of this base of 1.4. So let's see if my calculator will help me out here. This is a pretty nasty base. So how did we get that base anyway? Oh, it was this number raised to the 12th. So I can do that. I can put that into my calculator. Just turn it on. It's, oh, here it is right here. So let's take log, LOG. Oh, I forgot. I got to change base. Never mind. It's not going to, you haven't learned how to change the bases yet. So we'll come back to this after Wednesday's class. Sorry. I'm ahead of myself. I don't want to confuse you anymore. Then maybe you're already confused. Who knows? So let's see now where this all leads. If we come back to this picture of f of x equals 2 to the x, and I asked you to sketch, let's suppose you had no idea what the inverse function is, and I asked you to sketch the inverse function. Where might you start? What would you start with here to try to sketch the inverse function? Yeah, Ben? Yeah, y equals x, because you know that it reflects along the line or over the line y equals x. So you try to get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. You try to go right through like that all the way up. And usually this is a dashed line, so sorry. And this is a little off here on this end. So it's hard to get that exactly where it belongs. So there's the line y equals x. And you know that this graph reflects across that line. So we know one of the points on all of our sort of vanilla-like exponential functions where we're not doing any transformations, it's like a parent function. We know it always goes through 0, 1. So if we go through 0, 1 on a f function, its inverse is the log base 2 of x, because this is f of x equals 2 to the x. Notice your base is the same. So what do we know about the point that we would find on the inverse function? What would its coordinates be? Let's see. Remember the range for our exponential, the range is all positive numbers. So what must be true for the domain of my log function? All positive. So I can't put a -1 into my log function. 1, 0, right. Remember that all that happens is that the input and output swap places. So I know 1, 0 is a point on my log function. There it is, 1, 0. So let's pick some more points. How about what was so nice about the point 1, 2? Remember, if your original exponential function is not being transformed in any way, the value at 1 always gives you the base. This is 2 to the x power, because when you raise 2 to the first power, you get 2. So whatever your output is at 1 on your exponential always gives you the base. So in this case, the corresponding point in the log function is going to be 2, 1. Because if you take the log base 2 of 2 and you lift off the exponent, you get 1. Log base 2 of 2 is 1. So now I've got that point, 2, 1. There I go. And now the next point might be 2, 4 on my exponential function. It will be 4, 2, because the log base 2 of 4, since I know it's a base 2, I can write that as log base 2 of 2 square. And when I lift off the exponent, I get 2. So I got 4, 2, and 8, 3, and 16, 4. 1, 2, 3, 4. So I've definitely got this part of my inverse function going. It looks like it, but I haven't finished this off because I haven't done any of the swapping of the coordinates for the part of this function that's less than 0. So let's see, when I have -1 and I put that into my exponent function, I get 1/2 for my answer. So when I swap, I get 1/2 -1. So log base 2 of 1/2 is -1. My output can be negative, but not my input. So where am I? I'm at 1/2, which is halfway between 1 and 0, and I'm down at -1. And then at 1/4, I'm at -2. So as I get closer and closer to 0, this gets closer and closer to my y-axis. And that is my inverse function, log base 2 of, if you want, you can call it y equals x, because y would be the output from your exponential function. Okay, so logs, look at this. The inverse function of 2 to the x only happens in the first and fourth quadrants, right? Because its domain can never be negative, so you'll never use the first quadrant or the third quadrant. And your output, so your input's all positive and your output's all positive numbers. So that's where you come into the fourth quadrant here with your negative inputs and then your positive inputs for your first quadrant. All right, so I think you're all set for your class activities. Have a grand time. You didn't finish number 1? What about number 1? No, because of the base. But we couldn't do it on see, because our calculator only does base 10 and base E, and that had a base 1.0, right? So on Wednesday, we're going to see how to change the base, and then we'll be able to do it.